All right, so I want to wrap up our discussions of set theory and move on to propositional logic. And I need to talk about functions, so I'm going to do that as part of our wrap up. But any questions on anything before we get started? Has anybody looked at the homework that's due Friday? So there's 3 questions from chapter 1 that relate to set theory, unions, and summations that we've already talked about. And then the other questions are from chapter 3, so we're going to go over that stuff today, and we'll look at those questions together. But it's always a good idea, if you can, to at least look at the homework ahead of time, so that as we're talking about things, you can think, oh, okay, this is related to that homework question that seemed weird. All right, let me talk a little about functions. So we've encountered this idea of ordered tuples or ordered triples, where instead of a set, which is an unordered collection, we have, say, a pair of things, A comma B. And the idea is this is not simply a set of A and B, it's a deliberate pairing of A and B, where A is somehow the first thing in our tuple and B is the second. So classic example is Cartesian coordinates. You have a point, you give it x and y coordinates, and you can express it as parentheses x comma y. And the order of x and y clearly matter, because if you switch them, you've got a different point in general. So that's a tuple. So thank you. So let's think about the idea of a function. So a function f, and we usually write f colon and then 2 sets with an arrow in between. And so this is a mapping or an assignment, or maybe an association of an element B, which we write as f of A, where B is contained in B, for each element A contained in A. So the straightforward way of saying this is, for every element in A, we have a unique element in B, an element in B associated with that A. It doesn't have to be unique. So for each element A in the set big A, we have exactly one element B in the set B associated with that A, and we call that f of A. And so, for example, f of x going from the reals to the reals, and defined by f of x equals x squared. So we can pick any element in this first set, any real number, 2.0, and this mapping associates an element in this other set, which is also the reals, associated with 2, in this case the value of 2 squared, which is 4.0. It also associates with the number negative 2 the value 4.0. That's perfectly allowable. You can have multiple things going to the same thing. Okay, it's still a good function. What's not allowable is if, for example, we associated 2 things with a number 2. If 2 could map to a 4, but it could also map to a 75. Okay, that's not a function. So that's the vertical line test you do in math classes. right? So there has to be exactly one thing associated with everything in A in this case. But you could have multiple things going to an element in B. Okay, so there's terminology. A is the domain of F, and B is the codomain of F. F of A is what we call the image of A.
Is this kind of like linear algebra mapping?
Could be, yeah. That would be a good example of a function, but it's a more general concept here.
I'm sorry I'm late.
That's okay. I got you signed in now. So f of a is the image. So think of a light shining on something and it creates a shadow, right? So a is the original thing and the shadow is the thing that it's being associated to. So f of a is the image of a, and a we can call the pre-image of f of a. So the thing whose image is a. And we'll sometimes write f of big A, which is the set of all f of, it's not a set. Yeah, it is a set. It's the set of all f of x, where x is an element of A. So f of big A, where big A is a set, means the collection of f of everything in that set. So take every possible value in A and find f of that, and you get a bunch of things in B. Okay, that's a set. So that's called the range of f. It's sometimes also called the image of f, but I'll use the word range. And we sometimes say f maps A to B. And we can define lots of functions, right? We already did one, f of x is x squared. We could do f of x equals the square root of x if we're careful. If x was the set of positive numbers, this can be a well-defined function. But if x is allowed to be negative, there is no square root of -1 unless we're talking about complex numbers. So the choice of the domain and the codomain is critical to very basic things like, is this a function at all? We could have f of x going from the set of integers to the set of integers, where f of x is just the first digit of x. That's a weird function, but there's nothing wrong with that as a function. It could be the last digit, it could be the sum of all the digits. Or we could have f of x equals 1 if x is even, and 0 if x is odd. Is it a function? Yeah, if we define this from z to z, it associates with each integer a value in the set of integers. In this case, either 0 or 1. So that's our even-odd function. So what do functions have to do with sets other than the fact that they map from a set to a set? Well, it's an association. It's saying with each element in set A, we identify an element in set B. So we can think of a function as a collection of tuples where in each tuple the first element is something from A and the second element is something from B, which we associate with that element through F. Well, have we seen something like this before? Tuples where the first element comes from one set and the second comes from another? What were we talking about? That was a cross product or a Cartesian product. So this is a subset of A cross B. So the Cartesian products of two sets is a whole bunch of tuples, and if we pick a subset of that, it might be a function. If we have a function, it corresponds to a subset of that. And a subset of that could correspond to a function. So let's restrict our universe. Suppose T is our universe and it's the set of things from 0 through 16. And let's say f of x equals x squared if x is less than or equal to 4 and it's 0 otherwise. So f of 0 is 0, f of 1 is 1, f of 2 is 4, f of 3 is 9, f of 4 is 16, and f of 5 and everything else is going to be 0. So we could define this function as the following ordered pairs: 0, 0, 1, 1, 2, 4, 3, 9, 4, 16, and then 5, 0, 6, 0, and so on. And that set of 17 elements where each element is a tuple has exactly the same information as this function f. So think about a more interesting function like y equals cosine of x. If we wrote the set of tuples corresponding to that, that would be a subset of r cross r. If we did y equals natural log of the absolute value of x, that would be a different subset of r cross r. And some subsets aren't actually functions, right? We could have a subset that we could, for example, include 2, 5 in here, which says that with 2 we're associating both 4 and 5. Well, that's no longer a function, right? But some of these subsets will be functions. So cosine, sine, logarithm, square roots, the happy function which tells you whether or not your lottery number is going to come out on a given day of the calendar starting with January 1st, year 0. These are all functions, and guess what? They're all subsets of r cross r, which means that if we simply write the power set of r cross r, which is the set of all subsets, that contains every possible function of real numbers we can ever think of, which is kind of cool, because that's a nice succinct representation. But that's every function from reals to reals. So we'll come back to that a little on Friday when we talk about limits of computation and how r is fundamentally bigger than z. All right, let me throw one more batch of terminology at you. And this is generally really confusing to most people, but we'll try it anyway. We can classify characteristics of functions, and we want to talk about characteristics in terms of how it maps things from its domain to its codomain. And I want to describe some fundamentally different situations. So let's think about f going from A to B. And here's our set A. And here's our set B. And we know that for every point in A, we get some image in B. So this maps over to here, and maybe this point maps over to here. Okay, so a first distinction we can make is, do different points in A always map to different points in B, such as we've drawn here? Or is it the case that sometimes we find two or more points in A that map to the same point in B? Now this is still a function whether this line is here or it maps somewhere else. Right, as long as with each thing over here we associate something over here and only one thing. But this is a fundamentally different type of function when we have two things mapping to the same value over here. So we have a term which is injective if unique values in A map to different values in B. Let me say if different values in A map to different values in B. So if it's true that anytime you pick two things in A that are different from each other and you map them, you get to two different points in B. If that's always true, then this function is injective. This is also called one-to-one. And it's just a property that functions have or don't have. If it doesn't have this property, then it's not injective, it's not one-to-one. So example, f of x equals, let's do f from reals to reals, and f of x equals 2 times x. Well, if you pick two numbers that are different, when you multiply by 2, you're going to get two numbers that are different from each other. Doesn't matter what the numbers are. 5 and 6 will take you to 10 and 12. Those are different from each other. So f of x equals 2 of x, this is injective. The classic example, f of x equals x squared, that's not injective. Because 2 and negative 2, those are different numbers, they both take you to 4. Right, so you have at least two arrows colliding over here in the codomain. So x squared is not injective.
Is non-injective also like onto? You say one-to-one?
No, so onto is the second thing we're going to talk about.
Oh, okay.
So injective or not injective, or one-to-one or not one-to-one. F of x equals sine of x, that's another non-injective function. Because 0, 2 pi, 4 pi, negative 6 pi, all of those, the sine function takes you to 0. So you have lots of arrows coming to the same point. So injective basically says, does every arrow go to a different point?
So if you restrict, say, f of x equals x squared to just the real numbers from 0 to infinity, would
Yes,
that then be
then it's injective, absolutely, because every number in the domain takes you to a unique number in the codomain. Right, so these definitions critically depend on what the domain and sometimes the codomain are. All right, so the next concept is surjectivity or onto-ness. So again, f goes from A to B, and there's A, and there's B, and we're mapping points. Okay, if every point in B is the image of something in A, then we say f is surjective. or we say it's onto. So surjectivity means everything on the right-hand side gets mapped to by something. Everything on the right-hand side has an arrow pointing to it. If we have exactly 5 points in B, this is not a surjective function if we've shown all the maps for elements of A. But if every point has at least one arrow, that is surjective. And we might have, multiple things pointing to points. If those are the only 5 points in B, it's still surjective. As long as everything has an arrow going to it, it's a surjective function. This just happens to not be injective because we have different points mapping to the same point over here. So they're different properties from each other. And you can think of this in terms of arrows, if you sort of keep this picture in mind of arrows going from A to B. Injective means every point in B has at most one arrow pointing to it. So let me flip back to our injective map. Suppose we have other points in B like this, and suppose this one, doesn't point to that one. This is an injective function, right? Because different points are mapping to different points over here in B. The fact that some of these points aren't mapped to has nothing to do with injectiveness. Okay? Every point has at most one arrow. One arrow, 0, 0, 0, 0, 0, 1, 1. That's injective. All right, surjective says every point in B has at least one arrow pointing to it. Every point has an arrow, it's surjective. This point has 5 arrows, that's okay, as long as it has at least one arrow. Okay, what's the sweet spot? Bijective. Every point in B has exactly one arrow pointing to it. And in that case, your function is going to be injective and surjective, and we call that bijective, or one-to-one onto.
Do you have any examples of functions that are not subjective?
Yes, and those are pretty easy to cobble together because it depends on this codomain. So for example, f of x going from the integers to the integers, there's no value over here that maps to the number 5 because there's no integer whose square is 5, so that's not surjective. If we go from the reals to the positive reals, then this is a surjective function. If we go to all reals, that's again not surjective because there's no real that maps to -1. And if we restrict to the positives, this would be injective but not surjective. Our favorite nicely behaved function, f of x equals x, that's injective and that's also surjective. Takes every number to its own value. So that's bijective. Bijective functions in some sense are, well, I don't know what they are. They're cool though. It basically gives you a one-to-one correspondence between things in A and things in B. Everything in A maps to exactly one thing in B, and everything in B can be associated with exactly one thing in A. Right? And that only happens if both of these conditions are true. And bijective functions are nice because they're invertible. It means that we can define a function going the other way from B to A, and we're guaranteed everything in B has a function value, or an inverse function value, and that different things in B will go to different things in A. Why? Because that mapping in the other direction was injective.
You panned out the definition.
Yeah. So every point in B has at most, at least, or exactly one arrow pointing to it. And we don't need to get too hung up on these. There's sometimes a short answer question on the exam about, you know, is this function injective or surjective? But mostly we want to understand bijective mappings or functions because they're going to be useful when we talk about one-to-one correspondences. And this is what we were doing with Hillbridge Grand Hotel. We found injective functions between the set of guests and the set of doors. So each guest went to one room, and each room had at most one guest in it, and so on. So we can analyze functions using these notions.
So it seems to me like there could be a little bit of confusion when you say one-to-one function, that's an injection, and one-to-one correspondence is a phrase that you're using.
Yeah, so a function is a mapping or an association or a correspondence. We could think of different terms for what a function is. But one-to-one correspondence will mean the same thing as, well, okay, so let's be clear, since we're being a little mathy in 215. If I say there's a one-to-one correspondence between two sets, it means there's an injective function between them.
Injective?
Bijective.
Bijective.
Yeah. So we can think of sets as being having a one-to-one correspondence means each element here can be associated with one element there. That means there's a bijective function from one set to the other.
But if you say one-to-one function, you're meaning injective.
One-to-one is in, sorry, I should say one-to-one and onto. You're right.
That's what I'm saying. One-to-one function is an injection. One-to-one correspondence is a bijection.
Okay, is it really?
Well, I'm just saying that's what the terminology is out there.
Yeah, so let's not use the words one-to-one correspondence. Let's stick with injective, bijective, surjective mappings.
Works for me.
Yeah, because that is a changing in the terminology. All right, let me make a couple of comments about matrices. Any questions on functions? We'll be using them more than we'll be getting worried about definitions like this, but I wanted to mention them anyway. Let me just mention matrices, because you take linear algebra at some point or now, but we should at least mention them in a discrete structures course. So what is a matrix? It's a big set of parentheses with things written in usually a two-dimensional pattern. Okay, that's my very scientific definition. So here's a typical matrix: 2, 4, 3, 7. And these pop up in ECS 120 when we do the dreaded KVL, KCL. Depending on your teacher. So we can do math on all kinds of things. We normally do math on whole numbers when we first learn about addition and subtraction. And later we do math on fractions. We add 2/3 and 5/8. And later we do math on real numbers, and we use decimal points. And when we get into more advanced topics, we start doing math on complex numbers, right? So if you've encountered I as a square root of -1, we can talk about, you know, I plus 1 times I minus 3, and so on. But we can do math on all sorts of things. We can do math on, you know, types of food at the cafeteria. You know, we can define a salad plus a soda equals a cookie. And, you know, there's nothing wrong with that. Is it useful? I don't know. So one thing we can do math on is matrices. And it turns out doing math on matrices is very useful. So the things we operate on are these generally two-dimensional arrays of numbers. They could be real numbers, they could be integers, they could be complex numbers, they could be functions, they could be all kinds of things. But we'll just stick with real numbers, mostly integers. And we can define what it means to add these things. So if we have something like 1, 2, 3, 5 plus 2, 2, 4, negative 6, we just add element by element. This is a 2 by 2, this is a 2 by 2. We're going to get a 2 by 2 matrix where this is 1 plus 2, this is 2 plus 2, 3 plus 4, and 5 plus negative 6. And that's going to be another 2 by 2 matrix, which is 3, 4, 7, and negative 1. And that's not too hard. That's sort of a first guess what you'd think of for addition anyway. And we can do subtraction the same way. Just subtract the elements. It gets interesting when we talk about multiplication. And we could multiply by just multiplying 1 by 2, 2 by 2, 3 by 4, and so on. But that doesn't turn out to be the most useful way to multiply. So we have this peculiar thing we do when we do multiplication of matrices. And if they're both 2 by 2s, we're going to get a 2 by 2. But the first thing we do is we pick out the first row and the first column, and we do what we can call a dot product. We multiply the first element by the first element, second by the second. And that's going to be element 1, 1 of our matrix. So this upper left element is going to be 1 times 2 plus 2 times 4. And for the element in the first row, the second column, we take the first row and the second column, and we do the dot product on those. So it's going to be 1 times 2 plus 2 times negative 6. And we can do that everywhere. So second row, first column is going to be 3 times 2 plus 5 times 4. And then the second row, second column is that dot product, so 3 times 2 plus 5 times negative 6. Now that's perhaps a seemingly weird way to multiply things together. That's what it means to multiply two matrices. And if you, how many people did this did something with matrices in 120? Okay, we don't always go over it. It turns out that if you I don't want to give KCL flashbacks here. Turns out that if your first matrix is a collection of numbers and your second matrix is a column of I1, I2, I3, for example, and you multiply them out, what you end up with looks very much like the set of simultaneous equations you end up with when you're trying to solve a circuit using KCL or KVL. And so it turns out with this notion of multiplication, we can use matrices to solve simultaneous equations. And that's one of the big things matrices are used for, and it's why they pop up so much, especially in computer science. So suppose we want to solve a pair of equations. It turns out we could do the following. We can write a matrix equation. And if you multiply this, the first row, first column is going to be 5 times x plus 7 times y. Hey, that's right there. And the second row, first column, is going to be 1 times x plus negative 1 times y. That's x minus y. Hey, that's right there. So this product is going to be 5x plus 7y and x minus y. And if we ask to make this matrix equal to 12, 2, that can only happen if 5x plus 7y is 12 and x minus y is 2. In other words, it can only happen when x and y solve this pair of equations. So if we write an equation like this, the question is, can we figure out what x and y are? Well, we can think of this as a pair of matrices. Let A be a matrix 5, 7, 1, minus 1, and let B be a matrix 12, 2. We could write, and let X, big X, be a matrix XY. We can write this equation as just big A times X is equal to big B. I'm just renaming my matrices. And so can we solve this equation for X? If we do, we know what the value of X and Y are. Well, if it's plain old algebra, this is easy to solve. Just divide both sides by A. All right? Fortunately, there's no division with matrices. It would be a really different world if there was. But we don't have a quick and handy algorithm for dividing a matrix by another, and in fact, it's not even well defined in general. But we do have a way to define the inverse of a matrix sometimes. So 1 over A is written as A with a minus 1. Okay? And it turns out if we take A inverse and multiply it by A and multiply by X, that's the same as A inverse times B. And A inverse times A ends up being something that acts like 1. It's something we call the identity matrix. Identity matrix is just a bunch of 1s on the diagonal. This is not on the test. We're just talking now. And the identity matrix turns out if you take the identity times X, you just get X. So this turns out to say X is equal to the inverse of A times B. When we know how to multiply matrices, all we got to do is figure out how to find this inverse of A. And that's a trick. So if you got a calculator with a good number on it, it'll do inverse matrices for you. And if you're in linear, you learn how to do this by hand, and there's a variety of ways to do it by hand, and some of them basically come down to solving simultaneous equations. Some of them come down to making modifications on rows in the matrix and putting one part of the matrix in a certain form, and then your answer is on the other side. But there are ways to find inverses of matrices. And if you find the inverse of A in this case, just multiply by B, and you've got your answer. And solving simultaneous equations is really, really critical in life, in computer science. Okay, this is how you do robotics. This is how you do games. This is how you do rendering of images in a graphics display. This is how you balance a portfolio on Wall Street. This is how you do all kinds of things. And since solving equations simultaneously comes down to finding the inverse of matrices, if you can find the inverse of a matrix really efficiently, you've got a really good tool on your hands. Okay, these are the kinds of things that change the world. So that's an area of a lot of work. And we won't talk about how to find the inverse of a matrix. It's another big long set of algorithms and steps that you can do a bunch of different ways. So one other thing to note about matrices, if you take A and you multiply by B, generally it's not the same thing as B multiplied by A. So we always talk about commutativity, and it's like, why are we talking about that? It's obvious, right? But this is an example where it's not commutative. And that can cause some issues in life. But if you just take these two matrices and multiply them in the other order, you usually get something different. All right, last comment on this notion of using a dot product to multiply these things together. Right, we can write this as a summation. And I'm not going to do that because it's a nightmare as far as subscripts, and it confuses more than it enlightens. But basically, we could write a summation because we're taking the first element in this row and the first element in this column, multiplying them together. Take the second element, multiply them. If there were more, take the third and the third, multiply them, and then sum them all together. Right? That's just a plain old summation. And we have to do that summation of n things for every element in this row, every element in the next row, every element in the next row. So if you have an n by n matrix, and you want to multiply by another n by n matrix, to find the element in the first row, first column, you have to do n multiplications and additions. Right? First element times first element, second times second, third times third. You're going to have to do n operations to find the value of this resulting element. And how many elements do we need to compute in the output? Well, an n by n matrix has n squared elements, so we're doing n cubed operations. So a 10 by 10 matrix takes 1,000 operations. A 100 by 100 matrix takes 1,000,000 operations. 1,000 by 1,000 matrix takes 1,000,000,000 operations. So matrix math gets expensive, and that's another hindrance on, you know, anything that depends on matrices, which is most stuff. So we're always looking for better ways to manipulate matrices. All right, so any questions, concerns, comments?
You said if you have an n by n matrix,
Mm-hmm.
to find the number of operations that you would use to get one element of the product matrix would be n? Seems to me like it would be 2n minus 1.
It depends what you call an operation. So doing a multiplication and adding to a running sum, I'm thinking is one operation. But yeah, it would be 2n minus 1 because there's n minus 1 additions.
If you're talking about each addition being an operation.
Right, and each multiplication.
But
Yeah.
you're thinking of an addition multiplication combination
Right.
as one.
Mm-hmm.
Okay.
Yeah, and I'm thinking of it kind of from a coding perspective. We're going to have a loop that goes n times. How many times do we go through that loop?
Okay. I understand.
And that's what I'm really getting at. And we'll put some more meat on that later when we start talking about order of complexity. And that'll deal with the constants. But yeah, thanks. All right, so let's take a 5-minute break. Let's come back at 1:20. We'll start talking about propositional logic. And this will be a totally new topic. And the matrix stuff, don't get bogged down on it, right? You've seen it before. I just want to kind of reintroduce it so we can refer to it as needed. Same with the functions.